Start my recording and go full screen here. Okay. Need to automatically get it to duplicate the slideshow. All right. All right. So we're going to start talking. If you looked at the homework, you saw this already. Introduction to the Laplace transform in circuits. Okay. So you guys saw the Laplace transform in differential equations, most likely, right? So what did you use the Laplace transform for? What is it? What do you do with the Laplace transform?
You change the domain of your function to make a differential equation easier to solve.
Change. That's it's very well stated. You change the domain of your function to make it easier to solve. You go from the time domain to this S domain, and basically your differential equations became algebraic. Okay. So Eli, for instance, and others have asked the question before. Well, all right, what do we do when, if we needed to solve for the transient condition in some crazy circuit like we just had? Like you guys just did some crazy circuits, like crazy in the sense that there were 5 capacitors and 2 inductors and all that kind of stuff. That would be a 7th order system, what I just said, right? Think about that. So 5 capacitors and 2 inductors would be a 7th order system. All right, no one knows how to solve a 7th order differential equation. All right, there's no need to. All right, but I could do a Laplace transform and deal with that. And the Laplace transform idea is very closely related to everything we've talked about when it comes to this idea of impedance, and they unify with each other. But Laplace transform is a little bit more general. All right, now sine waves have a special place for us, though, which is why we spend time talking about impedance. But we're going to relate the Laplace to the impedance idea here for a second. So I say a circuit is a dynamic system. What the heck does that mean to say that it's a dynamic system? In other words, if I gave you this circuit here, here's R1, here's R2, I'd call that kind of a static system. So I'd call this guy static, and I would call this dynamic. What's the difference?
The capacitor.
Yeah, what about the capacitor? What does it do that changes in things?
It's got the transient effect that it has at DC, where it's has its effect.
Yeah, basically the capacitor, if you had to say I equals C dV dt, all right, that gives me a transient response. If I had a DC input. What, in words, what does that mean? What does I equals C dV dt mean? I say, well, it currents the rate of change of the voltage. Basically, what does it say physically that I equals C dV dt?
0.
The current depends on the rate of change of the voltage.
Current depends on the rate of change of the voltage, yeah. And more importantly, what that means is capacitors don't like to change their voltage quickly. Inductors don't like to change their current quickly, all right? And so if I just applied a voltage all of a sudden to my static circuit right there, what would the current be everywhere? As soon as I apply at time t equal to 0, if I turned that voltage source on, the current would immediately ramp up to its final value. Boom, that's it, okay? In the case of the top circuit, the dynamic circuit, would the current immediately get to its steady state value?
No.
No. And what would its steady state value be if that voltage source was just a DC voltage source?
0.
0. The steady state current would be 0. Now it doesn't immediately get there. In fact, it'll be really, really big initially, and then it'll basically drop down. Okay. So dynamic basically means that everything here changes with time. All right. So in general, this guy, there's a differential equation that describes it. If I wanted to figure out what's V sub C of t, I would find that RC dV C dt plus VC of t is equal to V. All right. That's what I would find for this thing if I wrote out the differential equation. What is true about this circuit, no matter what type of input, no matter what V is? In fact, let me just say V is V of t. It could be anything. Okay. What is true about the input V sub C of t? It's got 2 pieces.
It's constant.
Well, so it's not constant. So Eli just said it here in the room. There's a particular solution and a homogeneous solution. That's the math way of saying it. What's that mean to an engineer? What's a particular solution versus a homogeneous solution?
transient versus steady state.
Yeah, this guy here is transient. That's why Gideon is the star. He steps up there when needed.
I don't understand how transient is easier mathematically when you describe it as
It's-
more complex. Like it's
The transient's not easy. I don't know if I ever said that.
I mean, it's just A e to the st, and I feel like you have to do more work to get.
Well, you got to do it. Trust me, if you had to do the transient response of a 7th order circuit,
You'd understand.
that'd be a lot of work.
Okay.
You want to guess the 7th order solution and then go through that whole. Yeah, it would be messy, right? I'm not saying it's easy, right? What I'm saying is we typically just don't care about it.
Okay.
All right, because think about it. How long has the power system been on? So like the power system that's connected to the wall socket. Yeah, it never turns off, right? Most of the time we're in steady state, right? So transient conditions don't happen that often. Now they do. Every time you connect something to that wall, there's a transient, right? But that let's say you're running the air conditioner for an hour. There's a transient for a couple hundreds of milliseconds, right? It, as a percentage of the steady state time, is really small. So most of the time we really only care about the steady state. In particular, we sort of broke it down and we said, well, for a particular type of input, namely sine waves, all right, the relationship for the steady state currents and voltages could be developed algebraically in a different domain, right? That's what we've been doing for the last roughly month, all right? We basically said, we'll take our inputs and we map them into the phasor domain. So if I gave you A cosine omega t plus phi, you map that into the phasor domain. What's the phasor for A cosine omega t plus phi?
A angle phi.
A angle phi.
Yeah, A angle phi. All right. And the implication when I do this is I got to map the whole circuit. I do the circuit equation in the phasor frequency domain, which means that I need to derive impedances Z sub C and Z sub L. One of those things, this was a key takeaway from the test, which I tried to give a hint on Wednesday was going to be there, right? What Z sub C and Z sub L require what? They're only true at one what?
Frequency.
At one frequency, right? So 1 over j omega C and j omega L. And we derived those things assuming we had this time domain input. And we said, what does the steady state look like? We went into the equations I equals C dV dt, V equals L di dt, and we derived these things, all right? Once we do the analysis in the phasor domain, what do? Well, we jump back into the time domain, which is the real world. In other words, there is no such thing as an impedance. An impedance is a model that helps us think about what's happening in the real world, okay? Like I always say, stick your hand in the wall socket. What will you feel? You'll hear, you'll feel the voltage. Don't do it, right? But if you did it, you'd feel that pulsation, right? So there is a time domain variation. The real voltages in the real world are typically sinusoidal, and currents are typically sinusoidal. So what we sort of summarized, we basically said, all right, we derived this before. I said if I had this circuit, right, and I said I put a voltage across this thing, all right, V of t. If I put V of t across this thing, we figured out the current by saying I of t equals C dV dt, all right? And I got the steady state result, right? If V of t was V cosine omega t plus phi, all right? What I found in the end is that I of t was this thing, all right? Omega CV times cosine omega t plus phi plus 90 degrees. Now, looking at that, what's the relationship between I of t and V of t? There's three things that relate them, right? There's an amplitude, a frequency, and an angle, okay? What's true about the frequency of that current and that voltage? They're the same, right? If I put in something that has cosine with a certain frequency, I get out cosine with a certain frequency, right? What about the amplitude of the voltage and the amplitude of the current? What do we see about that? So the amplitude of the voltage was V. What's the amplitude of the current? Omega CV. So we said the amplitude of I was omega C times the amplitude of V, right? And what about the angle of I relative to the angle of the voltage?
It's by 90 degrees.
Yep, plus 90 degrees. All right. And we summarize that with this expression, right? Z capacitor equals 1 over j omega C. And you can go through the rest of that derivation if you want to there. All right. That's all that thing was really saying, is that if I put a cosine, if I have a cosine voltage, then the current is going to have a different amplitude by omega C. And there's going to be a phase shift in 90 degrees. So I would get the picture that's shown right there. All right. And then we did these phasor diagrams. We're going to talk a lot more about phasor diagrams later when we talk about power, because that's typically where we talk about that stuff. All right. But we had these relationships, and they allowed us to, the constraint with these impedances, right? We said, if I jump ahead this, right? So the limitations of impedance is it allowed us to simplify the math greatly, okay? So imagine, like I said, try imagine doing mesh or nodal with I equals C dV dt and V equals L di dt. All right, be a disaster. It's great because it simplifies the math. Now you may not think the math is simple, right? I had complex numbers. It's not that the math, just think about doing the math with differential equations, d by dt's, right? Rather than doing j omegas. All right, it would be nasty. All right, so it's great at simplifying the math. It takes us into a weird world where we have complex numbers, right? But it simplifies the math. Now, there's two shortcomings of this guy. All right, and I want to see if you guys can figure out what they are. What are the shortcomings of impedance? There's two of them. In other words, it can't tell us the full solution. If I take this circuit right here and I say V, let's say V of t was equal to, I don't know, 3 cosine 100t plus 30 degrees.
If the frequency changed, you wouldn't be able to tell with our current model, at least.
Well, okay. Let me come back to what he just said. That's a pretty good statement. RC, here's what I would get if I did this, right? RC dV C dt plus VC equals 3 cosine 100t plus 30 degrees. Okay. Now, that's the way you really should solve this. Like, that is just the truth, right? If you want the true total answer to this thing, you have to solve this. All right. What is, in that sense, knowing this, what is one limitation of impedance?
That it doesn't take into account either the angular frequency or time. That's the main thing.
Takes into account both angular frequency and time.
But the phasors, well, it does take account to the angle, but
That's not a
It's only
limitation.
for a certain phase angle.
No, not quite. So the key point that I was trying to make there is, this is the truth, right? This guy has two parts to the solution, correct? What are the two parts? One is the steady state, and the other is transient, okay? If I do impedance, which one of those do I get? The steady state or the transient?
say steady state, because you care about steady state.
If there's nothing, if I see you in 10 years from now on the street and I ask you what you learned, the one thing I hope it will be is that impedance gives me only the steady state solution. All right. I'm just a key point, right? Two shortcomings. Doesn't solve for transient. And what we said is most of the time that's not a problem. We're okay with that because we said the transient's not usually that important. Sometimes it is important, right? It's not important until it is important. All right. And most engineers don't worry about that on a regular basis. All right. It doesn't solve for the transients. That's one shortcoming of it. There's one other shortcoming of it. What type of inputs were assumed to make impedance work? In other words, when I say
Sines and cosines?
sines and cosines. In other words, only sines and cosines where the only allowed are the only sources allowed. Now, sometime around 3:30 on Friday, you guys were saying, well, wait a minute. What if I had this one, I had DC. Isn't DC also a sine or cosine?
Yeah.
Right? What frequency is DC?
0.
Yeah, DC is basically a cosine with omega equal to 0, right? And we said, if you take that 12 cosine 0t, what's that? 12, right? So a couple of ways to think about that. If it never fluctuates, if it never varies, right? That thing is constant, right? So its period is infinite because it never repeats again, right? And it has a frequency of 0. So basically, we said two shortcomings. I can't solve for the transient case, and this guy only works for sine or cosines. Well, that's not the whole world of circuits, is it? Right? We got all kinds of other stuff. Like, so for instance, you do digital circuits. What's a typical input when you're doing a digital circuit? What's something you have? Square wave. You get clocks, right? Yeah, pulses. Yeah, you get clocks, right? You get a clock that's a gigahertz or something like that. What's a clock? Clock is a square wave, right? That basically just goes from low to high, low to high, low to high, low to high. If it's a gigahertz, it does that a billion times a second. That's not a sine wave, right? Right? So there's all kinds of other inputs that exist in the world. Now, to deal with those other things, what does that mean? Does that mean we have to go back to differential equations? Differential equations, I said, is the truth. They are always correct, right? So if I had a square wave, would I say, this is equal to V the square wave? I wouldn't want to do that either, all right? So there's another approach, right? So we have all kinds of other inputs that might exist, right? So I gave a couple of examples here. So 5 cosine 20t, right? We know how to deal with that one, all right? 5e to the negative 3t, well, that's possible. That could be this input, okay? 5u of t could be that input. Now, I'm going to hope that Yahoo has taught us u of t. If I said, what is u of t?
It is 1 for t equals 0.
What do I call that thing, u of t?
Unit
Step function.
Unit step function, yeah. All right, so he takes a value of 1 for t greater than 0. All right, so 5 times u of t is basically 5 times that thing, right? Now, 5e to the minus 3t, that would be an exponential. Does it decay or rise? 5e to the negative 3t. Decay. All right, all of those are possible inputs, right? How many of these work with phasors?
2.
1.
Couldn't we change it?
Well, all right, so
to the cosine sine?
this one,
Even yet.
how does that turn to cosine or sine?
Well, you just do 1 over e to the 3t and change e to the 3t to cosine.
You're thinking
It converts rectangular, which you can convert to phasor.
e to the negative 3t, you're saying converts to rectangular coordinates?
It's
It
not
doesn't have a
complex
J, so
That's
you
a
can't
real
do that.
number.
Yeah, it's not a complex exponential, so you can convert it into a sum
Yeah,
of signs.
that's a real number. Yeah, you guys have sitcom crossover problems between me and Yahoo right now. All right. So
Can't you break the negative into j times j, and then you have a imaginary angular frequency?
Yeah, but it would all cancel out.
this is why you guys struggle with the tests. The world is less complicated than you think. All right. I honestly feel bad for you because I did the same thing as a student. Everybody did this as a student. You start thinking the world's a lot more complicated than it is. Like that problem 1, I have a feeling after you saw my solutions,
Definitely.
yeah. This guy is purely real. If there's no j omega in that guy, in the exponent, he's purely a real number.
Okay.
All right, there's nothing I can do with that that's fancy. Now this guy here could be, I could turn this into 5 halves e to the j 20t plus 5 halves e to the minus j 20t. All right, No, you could have, that's an angle identity that you would get from Yahoo. All right. But e to the negative 3t is always real. All right. I could also say this guy is the real part of what? It's important to take a second to review.
Isn't it the real part of V?
The real part of what?
V of t.
Okay, v of t is real, 5 cosine 20t. So it's the real part of what? What complex exponential would that be the real part of?
5e negative j to the 20t.
5e to the j 20t. And you would see that by saying it's the real part of, so you take e to the j 20t times cosine, so that would be 5 cosine 20t plus j5 sine 20t.
So that 5e to the negative 3t, is that a constant since it's a real value?
What makes something a constant? What does it not? What does it mean to be a constant?
Not dependent on time.
Not depending on time.
Okay.
So e to the negative 3t depends on time, right? He would decay with time. Okay. All right. Yeah. So I know so this, you're in a fragile place of learning all sorts of new things, right? So I don't try to use the complex exponential very often. I leave that for Yahoo to deal with, although we are implicitly dealing with it on a regular basis. All right. I try to, you guys have enough troubles with just the keeping impedances straight and all that kind of stuff that I want to make sure we don't get too fancy. All right. But one day it should all kind of come in place. All right. The point that I was trying to make here is that, you know, the inputs we have, if I had this guy, this is the only one. When I asked that question, we went off on a tangent there. But V of t, the only one that we can deal with phasor-wise right here is really this guy. He's the only one that can deal with. This is the only one that phasors can handle. None of the others can be handled using phasors, okay? And not only that, what do I not get if I use phasors for that cosine input?
Transient response.
Don't get the transient response, right? So I want to get that, all right? So what I can do is I can generalize the idea of impedance. And with that, I can use something called the Laplace transform, right? Which is what you guys have learned before. And there's actually two types of Laplace transforms. There's probably a million types of Laplace transforms, right? But when Laplace derived it, all right, he had a unilateral and a bilateral. So if it matters, this is the unilateral Laplace transform, which means that the integral there is defined to go from 0 to infinity. Don't worry your head about that, okay? Just call this the Laplace transform. Now, what this does so again, in words, what does this thing do? I guess I kind of wrote it there, but if you had to say, what is that thing? You guys get way too lost in the math, right? And I know why, but what is that thing doing? So if I take the Laplace transform, what this is here, this is the Laplace transform of a function of f of t, okay?
Takes us from the time domain to the frequency domain.
There you go. I guess I kind of have it written there, right? But I put in a function f of t and I get out a function f of s. And we write it capital F of s, okay? And we often say that s is frequency, and it is typically complex frequency, meaning j omega, okay? So in the real world where I have f of t, I have differential equations. In the Laplace world, I have algebraic equations. That's why you liked it in differential equations, because I went from differential equations to algebra, right? F of s stuff is algebra. Differential equations are differential equations. They're calculus, right? So it's calculus on the left. It's algebra on the right, all right? I think we all agree that algebra is better than calculus, okay, in general. All right, so how does this help me? All right, well, it helps me in a lot of different ways, right? But before I go into this. So basically what I'm going to say is I can generalize the idea of impedance using this idea of the Laplace transform by taking stuff in the time domain and converting it into this S domain. Now, to do that though, I want to try to remember some stuff that you did do in differential equations. So some common signals, so some common things that you saw a lot in differential equations. Okay, U of t. So U of t we called the unit step. We said he basically was, he jumped from 0 to 1 at time t equal to 0. Okay. So if I wanted to calculate the Laplace transform of that guy, I guess I'm going to call it U of S. All right. How would I do that? If I want to calculate the Laplace transform of that guy, of that signal.
Rest from 0 to infinity.
I integrate from 0 to infinity, U of t, e to the negative st dt. So when I'm done that, the thing is I'm integrating with respect to what variable here?
T.
T.
Time.
T. S is a variable, so I'm going to get out something that's a function of S. Okay. Now we're going to relate that S to frequency here in a little bit. Okay. But if I want to do that, that basically says, so, all right, how can I simplify? U of t is what? How do I simplify this guy? So I can actually, I can't integrate. What is, I need numbers. I can't just have U of t there, right? How can
Pull
I?
it out, right?
Can't pull out a function of time out of an integral of time.
Even if
Well, since we're going from 0 to infinity, you could just replace it with constant 1.
Yep, that's right. Yeah, since I'm only integrating from 0 to 1, well, U of t is just 1 there, right? In other words, this guy becomes the integral from 0 to infinity, e to the negative st dt. Now, I hope everybody remembers how to do integral e to the negative st. Yahoo would cry if you can't.
1 over negative s.
What is that?
1 over negative s.
Yeah, so I'm gonna say negative 1 over s.
E to the negative st.
E to the negative st. All right. And I'm integrating that guy from 0 to infinity. It's a definite integral. Okay. All right. Now, this is where Yahoo would also cry because I'm gonna make some simplifications that engineers like to make and mathematicians don't. Okay. So I got to evaluate that guy at infinity. So technically, I got to start doing limits, don't I? Really? L'Hopital, I don't want to do limits, right? So if I have 1 over infinity, what's 1 over infinity? 0.
Really small number.
0. Yeah. So that means that this guy is 0. If I evaluated infinity, I'm not going to do limits, right? Then I do minus. So minus 1 over s times e to the negative s times 0. What's e to the negative s times 0?
1.
1. So this guy becomes what?
1 over negative s.
Nope.
Negative 1 over s.
Nope.
1 over s.
1 over s. 1 over s. And what if I did the integral of 5 u of t? What would this become?
5 over s.
5 over s. Okay. There's a whole set of properties on Laplace transforms. You'll learn more about Laplace transforms in 3111, 3112, some combination of those two things. Okay. We use it a lot in a lot of places. Basically, what have I done? I've taken this u of t thing that models an input that we might have, right? What is this guy? First of all, okay, so I just said this guy's common. What the heck is that thing? So I have a function that goes from 0 to 1. What I said that models something. What does it model in the real world?
I want to say pulse.
Yeah, it could be a pulse, right? I mean, one thing that we know that it does is it could be basically this guy here. If I had a switch connected to a circuit, right? And I close the switch, right? That kind of thing is what makes that possible, right? So like if I hook this up to my circuit here, here's RC. Okay. This might be my U of t right here, right? At t equal to 0, this guy is nothing. And then as soon as, if I close that switch at t equal to 0, I'm going to get 1 volt if this was a 1 volt source. All right. So in other words, this guy models connecting a source up to a circuit. And it could be a pulse if I added to this guy, let's say another u of t that was somewhere else, shifted down, okay? Anyway, I don't want to get too lost in that. This is a common input, all right? What about e to the at? That's another common one, eat. What do I do with that guy?
You want to the answer or the step by step?
Yeah, let's do it. F of s.
Okay, integral from 0 to infinity.
Yeah, integral from 0 to infinity
E to
of
the
e to the at
down to e to the negative at.
e times e to the negative st dt. That guy would become simply what?
E to the at outside.
E to the what?
That's
How about e to the a minus st? Like that, dt.
yes.
Okay. I can't. My t's look too loopy. All right. So e to the a minus st. All right. So let's make Yahoo proud again. What would we do if we integrated that guy?
Negative 1 over a minus s.
Well, it would just, so 1 over a minus s, there's no negative per se, right? Times e to the a minus s t evaluated from 0 to infinity, right? So there's no negative there, right? So the way I think about this, if I want to check, I take the derivative, right? So if I took the derivative, I should get back to my original input. So take the derivative of 1 over a minus s times e to the a minus st, and you would get e to the a minus st. Too many words. All right. If you evaluate that guy, again, it's not particularly exciting. At the end of the day, you're going to get this 1 over s minus a if you evaluate that. All right. So the Laplace transform of eat is 1 over s minus a. All right. Again, not a result that's particularly exciting, right? And some of the to clarify, some of the results we've had are exciting, right? Impedance was an exciting thing for me because it meant I didn't have to do differential equations. It was exciting for me at least. All right. This guy I don't particularly consider exciting, but it's important. I can use it. If I had as an input to my system e to the at, I could use this guy. We're going to use it here in a little bit. All right. I'm not overly excited about solving differential equations though still. So I have a point for doing this, which I want to relate it back to impedance. All right, now then the other thing we can deal with, this is what you learned in differential equations. If I take the Laplace transform of the derivative, all right? So if I know, and we use this term, if f of t has a Laplace transform, that's what this little scripty L thing says. F of t and f of s, that's how I relate the function f to its Laplace transform f of t, right? So in other words, this guy is integral f of t e to the negative st dt, 0 to infinity. And I saw everybody start taking notes now because I'm doing calculus, right? It must be important, right? It's not, okay? You're not going to remember how to do this or this, all right? Doesn't matter. The result matters, okay? But you won't remember the steps, right? I don't like getting too lost in derivations, but there are some derivations that are important, right? So I want to make sure that we understand them. So this was the key result that you had in differential equations, right? Differential equation, you said, okay, well, if f of t has a Laplace transform f of s, if I tried to say, well, what's the Laplace transform of the derivative df by dt times e to the negative st dt, right? This would be how I do the Laplace transform of the derivative. You guys agree with me?
Yep.
Right, plug that in. How would I have to solve for that thing? I don't want to do it, but how would I have to do it? I got two functions multiplying each other. One of them is df by dt. Integration by parts. All right, winner, winner, chicken dinner, right? This guy is uv minus integral v du, right? where you would say U is,
I don't even remember that.
well, dv, you must be doing this with Yahoo, right? dv is df by dt, and U is e to the negative st dt, right? And you'd go through this whole thing, all right? If I did that, what I end up with is that the Laplace transform of this guy is S times the Laplace transform of the function minus whatever the initial condition value is for the function. Okay. You saw that in differential equations. You use it all the time in differential equations. Okay. We could derive that by doing integration by parts. Hopefully with Yahoo, you've been doing all kinds of integration by parts and you're ready to handle that. Well, guess what? We're not going to do integration by parts. Okay. That's a Yahoo thing. All right. We're not doing integrals. Don't start thinking we're doing calculus. We're not going to be doing any calculus, right? We're just focusing on this stuff. All right. We want the results of this thing. Now, in particular, where I could use this is I could say, well, what happens if I have that guy there, 5e to the minus 3t, and I wanted to find this voltage Vc of t? Okay. What would I do to do that? Okay, so what is the differential equation? We've written it a couple of times here, right? So V of t, first of all, so I've been writing it just because I know what it is, right? How would I figure out the differential equation here if I had to figure it out?
Well, with respect to voltage, KVL.
Yeah, I'd do KVL, right? I'd do a KVL around this loop, and I would end up getting, so RC dVc dt plus Vc of t is that, okay? So if I had to do this guy in the Laplace world, what would I do? So if you had to take the Laplace transform of this thing to solve it, I said V of t is this. What would this become? How would I rewrite this expression right here?
Which one? The
Integral of V of t.
Well, I don't have to. So here's what you did in differential equations. You said in differential equations, I turned that differential equation into its Laplace counterpart. So I replace V of t with what?
The Laplace transform of V of t.
The Laplace transform of V of t. V of s. Okay. This is what you did in differential equations. Right. What do I do? So what do I do with the other side of the differential equation?
Laplace transform again.
Laplace transform it as well. What's the Laplace transform of Vc of t?
S.
Vc of s, right? Vc of s.
Oh.
Okay. What about RC dVc dt? You guys are looking for something deeper here, right? If I take the Laplace transform of it, I go, all of my time domain functions become Laplace transforms. Okay. And what do I say with RC dVc dt? What is that? What do I do with that?
To S.
Well, I use this result right here, right? So if I have dVc dt, that's going to become equal to what in the Laplace world based on this result here? If I'm taking the derivative of the capacitor voltage, what's it going to be equal to?
SVC.
S times the Laplace transform of the capacitor voltage minus the initial condition of the capacitor voltage. All right, it says 0 minus. We know 0 minus, 0 plus are all the same, right? So I'm just going to write it that way. Now, how would I use that here?
So it's RCVS.
Yep, I'd say S R C times VC of S. And I didn't include the initial condition because I didn't want to. I said it was 0. Okay, if I had one, I'd have to include it. All right, but I don't. All right, so when I look at this guy becomes V sub C of S times what? How can I rewrite this expression over here?
Would be 2 RCS.
It would just be RCS plus 1 at that, right? So the way we rewrite this is we would say V sub C of S is equal to what times what? V sub C of S equals what times what?
Then just VS over RCS plus 1.
Yeah, 1 over SRC plus 1 times V of S, like that, right? V sub C of S is 1 over SRC plus 1 times V of S. Now, we derived a little bit ago what V of S was for this special type of input. 5e to the negative 3t. Didn't we derive something like that?
1 over S minus S.
The 5 over 2 S.
Yeah, we had et here, right? E to the at, right? That became 1 over S minus a. So what is 5e to the negative 3t? What is that going to be?
S plus 3.
5 over S plus 3. Okay, so this guy would become 1 over SRC plus 1 times 5 over S plus 3. Now, if RC was a number, which it would be in a real system, RC would be a number. How would you solve this? So let's say V sub C, whoa, not what I want. All right, V sub C of S is, I'm going to write it this way, 1 over SRC plus 1 times V of S equals 1 over SRC plus 1 times 5 over S plus 3.
Just multiply and use quadratic.
Yeah.
All right, so again, I'm going to take this as prerequisite. And so if you had this, right, and let's say SRC was a number, how would you solve this to get it back into the time domain? I'm going to say it's prerequisite because I don't want to spend a whole lot of time on it. It's not circuit stuff. It's not that important to me.
You have to do what we tell.
Who knows what to do?
Take back to the Laplace transform, inverse Laplace transform.
So I got to do an inverse Laplace transform, right? So what we did here is we took a differential equation, we converted it to the Laplace domain, then we basically got to undo it, get it out of the Laplace domain. I got to take an inverse transform. How do we take the inverse transforms of this stuff?
So it's both sides, VS, VCS, or V.
Well, I got to do both sides, yeah. But what's the key next step here?
You have to match it to a table.
I have to go to a magical table. I have to match it to a magical table. Yeah, there is a magical table, but there's a step before that.
You separate the right side to the two fractions.
I think I understand what did you say, 2 fractions?
Yes.
Okay, you got to do partial fractions.
Yeah, partial
All
fraction.
right, anybody remember that word? Partial fraction. All right, so basically this guy becomes A over SRC plus 1 plus B over S plus 3. And what do you got to figure out? You got to figure out A and you got to figure out B. All right. And if you go through that carefully, what are you going to find? Well, once I get back into the time domain without doing the math on it, and the math's not hard to do that, right? All right. So, but you basically would find it's A e to the negative t over RC plus B times e to the negative 3t. If I inverse Laplace transform that. All right. So that is something you guys have sort of seen before. I guess I should be really careful. It would be A over RC, I guess, is what it would really be. All right, but I'm not. It's just it's a constant times e to the negative t over RC. Okay. All right. Again, problem 2 of the homework gives you a differential equation, and you got to go and do this. Basically, it's just a refresher on what you did in differential equations. Right. It does it with a step input, I think. Okay. That's not really still the key thing. So in other words, if I have a weird input like this, I could use this, all right? But there's a couple of things that I like about this. This expression here, it says that the thing I'm looking for, which is a term I'm going to keep using, I'm going to call it output. The thing I'm looking for is equal to something about this circuit, right? This guy right here is something that came from the circuit. This guy right here is what I keep calling inputs. Okay. So what this says is the output is some function having to do with the circuit times the input. If I kept that in the time domain, it would be related to the derivatives of that. It's a complicated relationship there. But in the Laplace world, this guy is a nice, friendly relationship. All right, which I like, and I'm going to exploit that a little bit more as we go. But before I even do that and say, I don't even want to write I don't want to do KVLs and write differential equations, right? What was nice about using impedance?
You could use regular circuit analysis for it.
Yeah, I could base everything was Ohm's law again, right? So I want to go back to just everything being Ohm's law again and not have derivatives, okay? So I want to use that here. So let's say I have a capacitor, okay? And here's the current I of t and the voltage V of t, like that. Convert this guy to the Laplace world for me. I equals C dV dt. How would I write that? That's a differential equation, right? I of t equals C dV dt, differential equation. How do I write that using the Laplace transform? Go to the Laplace world. What do I replace I of t with? I of s.
Ah, yes.
Yeah, I of s. What about the other side?
T VS.
Say that again?
T S VS.
Yeah, so anytime I have let's look at this way. Anytime I have a d by dt, what does he get replaced with? That's maybe the takeaway of this guy right here. Anytime I have a d by dt, what do I replace it with when I do the Laplace transform?
S times whatever you have.
S, right? D by dt gets replaced with an S, okay? So this guy becomes SC, so S times C times V sub C of S minus C times V of 0, okay? And I'm going to make a special assumption that I don't have to make, but it's an assumption that we usually make, which is that VC of 0 is 0, okay? If it's not, then I have some more work to do, all right? But if it is, this guy is 0, okay? Now, that kind of looks impedance-y, does it not?
Somewhat.
What do I have? I have an I of S, and I guess I should just call it V to be consistent. I of S equals SC times V of S. That looks awfully impedance-like, right? So impedance we wrote was V sub C. Let's say I write it like this.
Oh, the impedance would be SC.
Not SC, but 1 over SC, right? Doesn't that look familiar? So this guy here, I'm going to say is my Z of S. This is my Laplace impedance. Boy, he looks awfully similar, doesn't he?
S is omega j, isn't it?
Yeah, or J omega, yeah. So it's awfully similar.
So it's like if we took Ohm's law and replaced the R with 1 over SC.
Yeah, which is basically what we were doing when we did impedances, right? So if I did this phasor wise, I would say the phasor V is equal to capacitor impedance times I, or 1 over J omega C times I, like that. So I got a very similar relationship here for this guy. Yeah, so if I did the inductor, right? Let's do the inductor. All right, so what would this guy be if I Laplaced it? So I'd have V of S. And what would I do with the other side of that equation? S, L, I of S. Now, technically, I'm going to say I of 0 is equal to 0. Doesn't have to be. Okay. Doesn't have to be. We almost always consider it that way. All right. If I really had to, we could plug it in. And there's basically another way of dealing with that. All right. But again, that's not something that gets us to the transient part. That's usually not all that important for us in circuits. Okay. Like I said, take it for granted right now. The math's going to look a lot better if I let the initial conditions be 0. Okay. Doesn't have to be. I'm not going to, don't worry about like, well, is the question on the exam going to be the one where it's not. All right. There's not going to be an exam question or a final exam question or a question you'll probably ever face in your life where you deal with that initial condition is not 0. Well, I won't do that to you. Okay. All right. That's not the trick. But looking at this again looks Ohm's law-ish, doesn't it? I have a voltage equals SL times I, right? Voltage equals something times current. That looks Ohm's law-ish, right? So that to me says this looks like some sort of a ZL times I of S, where, in the phasor world, we said V equals, well, let me ask you, what would I say in the phasor world? What would I write here if I had an inductor?
J omega L.
J omega L. All right. So SL J omega L. 1 over SC, 1 over J omega C. Based on that, it looks like we're making some jump here. And we're saying if we have sine waves as our inputs, what is S equal to?
Negative J omega.
Just equal to J omega. Okay. Now we're gonna deal with that. But basically what we found is the phasor is a special case of the general case. Laplace transforms are the general case. The phasors are sort of a special case. All right. And, we kind of use them interchangeably. Oftentimes in fact, I may have even said a couple of times that it's 1 over SC is the impedance, right? Because I think that way, all right, in general. So I might have said that before now. But basically what I've seen is, okay, now what this is saying is I can use this Laplace impedance idea. I can use it with any type of input, not just with the sinusoidal inputs, right? And then a resistor would be pretty obvious, right? V of S equals what? What would I Laplace transform that to? There's nothing fancy here, right? V of S equals
RI of S.
RI of S, right? It's just Ohm's law, right? Nothing fancy there. All right, so what that says is, all right, so could I do this? All right, so everything I did here I wrote a differential equation. I don't want to write a differential equation. I kind of like the impedance thing because I didn't have to do it, right? So what could I do in this case? Let's say, again, I have V of t, the input is equal to 5e to the minus 3t, okay? Let's say I wanted to solve for that guy, right? I wanted to figure out what is V sub c of t. What can I do instead of writing the differential equation? Well, what did we do when we did impedance instead of writing the differential equation? What did we do with the circuit?
Convert it.
Yeah, we converted it. We're going to do the same thing. We're going to Laplace the circuit. All right. If I Laplace the circuit, V of t becomes V of S. Okay. What about the R and the C? Well, the R is still what he was before. He's still R. What about the capacitor here? What would I replace that with here? 1 over SC. 1 over SC. And then I have V sub C of S. And just like in phasors where we solve for the phasor and then we transformed it back into the time domain, in this case, I would solve for the Laplace transform and transform it back into the time domain. Okay, it's the same basic idea as what we were doing before. Okay. All right. So let's keep going with this. All right. So if I wanted to solve for V sub C of S, how would I do this now? I can do it this voltage divider. Yeah, I can do it the same way I did before. Voltage divider didn't work with a differential equation. I don't know how I would do a differential equation voltage divider. That would be tricky. This guy I can do a voltage divider, right? I can say V sub C of S, because those are impedances that are in series. Help me out with that. How would I write that? V sub C of S is equal to V of S times. Yeah, so, okay, so voltage divider means what's the current in the circuit? V of S, we'll do it that way.
R plus 1 over SC.
R plus 1 over SC. And on top, I have 1 over SC, yeah, right? So the current in the circuit's V over R plus 1 over SC. And then you multiply that by 1 over SC. Now, in general, we leave these things as functions of S, which is what we're going to see. All right, we're going to see that more on Wednesday. All right, but looking at this guy here, so when I say leave it as a function of S, I want it to be ultimately a rational function of S. All right, so hopefully we'll go back to your math days. What does a rational function mean? If I have a rational function, what is a rational function?
No fraction.
Well, it is. So if I have a rational function, then it's a ratio of polynomials, right? So in other words, I have a polynomial of S on the top and the bottom. So what I would do here, what I typically do is I would multiply top and bottom by SC, right? If I multiply top and bottom by SC, what is that like multiplying by? 1. All right. So if I did that, what's that become? What happens to the numerator there?
VS.
Just becomes V of S. What's the denominator become?
RSC plus 1.
Yeah, SRC plus 1. All right. I didn't have to do that, but we often do that. We're going to do that a lot beginning Wednesday. Looks cleaner. All right. And we like polynomials of S, as we're going to see. All right. So that was, I mean, I would argue that that is a simpler approach than writing the differential equation. If I look at the circuit, I never have to do that. Okay. The other thing is, if I look at what I ended up with there, I said V sub C of S is 1 over SRC plus 1 times V of S. And I can plug in for that input that I chose there, V of S would be 5 over S plus 3.
Does that mean your current is 1 over SRC plus 1?
Well, we'll solve for the current here in a second. It wouldn't quite be the same thing, but it would be similar, right? So what do I have here? V sub C of S equals this guy right here, 1 over SRC plus 1 times V of S, okay? So what it looks like, I keep using this term, and I'm going to refer to it again. This guy is what I keep calling the output, the thing I'm solving for. My output is the thing I'm solving for. I'll say the V or I specifically that I am solving for, that I am solving for. And this guy I keep calling my input, which is the V or I am supplying. All right. In other words, there's a voltage source or a current source that's used as the supply for that circuit. What do I call this thing? I give this a name as well. All right. What this guy is sometimes we call this thing a transfer function. So we went over a lot of math concepts today, but for the most part, we're going to use the results of those math results, but you're not going to be doing calculus, right? All right, don't worry too much about that. Not doing really calculus, but we are going to be using the results of the calculus, all right? Why do you think I call that the transfer function? What would be the reason for that terminology? Anybody have any ideas? Any thoughts on why I might call that a quote unquote transfer function? Yeah, because it tells me how the input transfers to the output, right? And so oftentimes we use this picture here where I say I take the transform of the input like I just had, V of S, multiply that by H of S. So we do this block diagram picture where I say the input times this is the output. So this guy here is V sub C of S, which is equal to H of S times V of S. That result, that transfer function result's a really important one that we're going to use a lot of, okay? So let's say we can figure out all kinds of transfer functions from this thing. Actually, at least I can figure out 2 or 3, right? Let's say, so we'll get to Eli's question. Let's say I wanted to figure out I of S, okay? And my input was V, right? So actually, in reality, I want to figure out I of T, right? I want to figure out what the current looks like as a function of time. That says, take the Laplace of the whole circuit. So what do I do over here for the Laplace domain version of that circuit? I don't write C, right? What changes do I make here?
1 over SC.
1 over SC. So this guy becomes over here V of S. This guy is R. This is I of S. And this guy is BC of S. And I replace that with 1 over SC, okay? And C is a number, R is a number, right? Those would be numbers, all right? S is not necessarily a number, all right? S is a variable. I can plug in values for S, but usually it's left as a variable, all right? And we're gonna see why that's important as we go through the next couple of classes, all right? So looking at this thing, we already figured out that V sub C of S is equal to 1 over SRC plus 1 times V of S. Let's say I wanted to figure out I of S. How would I figure out I of S?
V of S divided by 1 over SC.
V of S divided by what?
1 over SC.
Nope.
R plus 1 over SC.
R plus 1 over SC. Right? The total impedance in that circuit is R plus 1 over SC. Right? So what does that become? Well, if I multiply top and bottom by SC again, that guy would become SC over SRC plus 1 times V of S. Right? And I could plug in the Laplace transform of the input of V of S. All right, so basically the bottom line, takeaway for you guys to start working in problem 3, problem 4, problem 5, right, is basically to write these transfer functions. All I got to do is say all the places I had J omegas before, what do? I put S. Okay, I put S. And all right, so some key takeaways here, right? So in this, sometimes we call the Laplace domain the S domain. The output's always an algebraic function of the input. That was the key reason. So my example, V sub C of S is H of S times V of S. All right. Oftentimes that transfer function gets called H of S, right? We got lots to say about that. So don't get your head too knocked up about all this stuff today. Key thing is probably that process there. So if I want to use this, I take the Laplace transform of the voltage or current, create the transfer function of the circuit by basically trying to map the whole circuit into the Laplace domain like I have here. And then I basically convert the Laplace transform of the output voltage or current to some sort of a time domain signal, right? The good thing about this is, again, what it means is that for any input I have, I can avoid writing the differential equation, all right? So it means no matter what. So previously we were saying, well, we only got away with that if we were looking at sine waves. Well, in this case, I can actually do this in a fancier way, and I can basically get rid of the differential equation for any input. All right. Now, we still typically don't look at any input. All right, but it's important. We might, right, and we can, right. Like so, for instance, I could have like the exponential input I was talking about here. That's not uncommon to have that kind of thing. I could have a square wave or something like that, right? So all that stuff is possible. But I want to make sure that we understand there is a special relationship that exists. So this guy should collapse to what I know if I have a sine wave. All right. So in other words, we said that if I had, so the capacitor impedance in the Laplace world was 1 over SC. And in the Laplace world for the inductor, it was SL. Well, in the phasor world, we had what? So this is the Laplace. In the phasor world, we had what? J omega C and J omega L. Okay. So somehow there should be a deeper relationship other than, well, let S equals J omega, and there is. All right. But again, it relies on some deeper math. All right. In the special case where I have A e to the AT, so some constant times e to the AT as an input. So if I had a circuit with a voltage source as e to the AT as my input, and this circuit has a transfer function, h of s, right? So what I did here, right? So I found a couple of different, this is one transfer function here from input voltage to capacitor voltage. And then there is a transfer function from input voltage to current, right? Those are two different transfer functions. They came from circuit analysis. So from looking at the circuit, I came up with two different things, okay? Because I was looking for two different outputs. One case, the capacitor voltage, one case, the current, all right? I'll get a different transfer function depending on which thing I'm looking for. So if that's the case, if I've said my input was e to the AT times some constant, what I would find is that the steady state output would be simply the transfer function evaluated at A times the input. Okay. Now, why is that important? All right. This can be shown. In other words, if I go through the math and I say, well, this guy becomes A or S plus or S minus A, and I plug that in and I do partial fractions and all kinds of crazy stuff. Basically what I find out is the steady state portion of this output is the input times H, the transfer function, evaluated at S equal to A. Now we covered a lot of ground here today, but where have you seen e to the something t before? You have seen it there. Where else have you where else are you seeing this? So previously, at the very beginning, you guys started saying some crazy stuff about complex numbers, right? E to the AT, you've seen basically that e to the j omega t, right? You've seen this guy before. You know things like cosine omega t equals what?
E to the omega t.
Related to e to the j omega t.
The real part of
cosine.
Yeah, it's the real part of e to the j omega t. It's also what? One half e to the what plus 1/2 e to the what?
E to the j
omega. J omega t, e to the negative j omega t. This is our mathiest day of the year. All right. All right. So
Is 1/2 like the magnitude?
You've seen that with Yahoo. Whether it's front of mind or somewhere buried in the bowels, it's there, right? That relationship. What I'm trying to say with that is, well, cosine omega t is basically two exponentials like that. Okay. How does that relate to this?
Well, if you group them, you can get A, like big, like capital A, not little a, like for the amplitude.
Doesn't this guy look like A e to the AT? If A was 1/2 and little a was j omega, right? What's important about this basically is that if I get this guy, the transfer function of this guy, v sub c of s, and V of S my input, right? What I found is that this transfer function, 1 over SRC plus 1 times V of S, okay? This guy right here, if I had said to you, let's do this with phasors, right? So let's say I got a sine wave input. And what would you have done if you did this with phasors? You would have said that I had the input voltage here is V. You would have said this is R. And you would have said this is ZC. I'm going to write it as 1 over J omega C. All right, here's V sub C of S. Write that, or V sub C of omega. Say it's V sub C the phasor, okay? I would have V sub C. What would I get? How would I approach that here? If I want to solve for V sub C in terms of V, how would I do that?
So it's just V minus VR.
It is, but it's a voltage divider, isn't it?
Yes.
Okay, so help me out. How would I do the voltage divider here? It'd be V
So V phasor over ZZ plus
R plus ZC, all times 1 over J omega C. And what happens if I multiply both top and bottom by J omega C like that? What would this turn into? It'd be 1 over J omega RC plus 1 times V. It's the same thing with S equal to J omega. Okay. What that says is you could basically do everything I gave you in the homework, just do an impedance. Okay. All right. Except do it with S and then plug in S equal J omega at the end. All right. That's my recommendation. So do it in terms of S and then plug in J omega. Now there's a reason why we do this. All right. I like looking at this stuff as a function of S because it allows me to start thinking about something called filters, where I think about a circuit and I say, well, what happens if I put in an input that has a particular frequency? What happens at the output? Does it get bigger or does it get smaller? Or is it the same?
So that's what the Laplace is used for, to analyze the output of a circuit.
Laplace is used for everything. That's the bottom line with it. I can use it for anything. If I want to find transients in 7th order circuits, it's my way to go. It's my way to do it without doing differential equations. Okay. I can also use it to look at filters. I can also use it to fry an egg. I can use it to do anything. Anything I want to do, I can do with the Laplace transform. All right. I didn't talk about it with initially because I constrained ourselves only to sines. The Laplace transform allows us to look at anything. And it matches when we look at only sines.
But it's a different domain than the impedance, right?
Turns out it's the same, right? The only difference is that S, it's the same domain, except what we're doing is we're limiting the meaning of S when we do it in phasor. I don't want to spend too much time on the math. I can talk about that separately, but I don't want to lose everybody on that.
I guess what I'm trying to
If I had to say what's the key takeaway here, what I would say is everything in the Laplace world is exactly the same as everything in the impedance world, except S equals J omega. Right? That's the key takeaway for today. Right? The depth and meaning of that we can maybe process a little bit more, but that's what you need to be able to start your homework. All right, let S equal J omega. So there's some meaning to that we'll try to process a little bit more over the next couple of days. Okay. All right.
I'm trying to see like the difference between